Welcome students. Today we shall study the properties of laser. Laser stands for light amplification by stimulated emission of radiation. The basic properties are spatial coherence, temporal coherence, high directionality, special purity, high power, short pulse duration. One by one, we shall study these properties. You see, what is spatial coherence? You know, when two waves are emitted, one is this and of same amplitude, one is this. Now, we see that both look similar and one may be like this also. So there is some phase difference, small, between these waves. Now, spatial coherence, it allows laser when two waves are coherent, it allows laser to be focused to a very small spot. Now, what does this mean? Uh, and what is its applicability? It enables applications such as laser cutting and lithography. Spatial coherence allows the laser beam to stay narrow over long distances. Now, of course, diffraction is there, but not much pronounced. We can compare some facts that due to this, it enhances the directionality. When a torchlight, you have seen torchlight, there is the filament, and the light rays they are emitted, but these light rays are in random directions. Of course, it's like this, but it diverges very fast. For example, we see the divergence of a laser beam by diffraction depends on the laser type, and it can be in laser can be on the order of 10 raised to power minus 5 radians. That means on the order of 2 seconds arc over a unit distance. This is extremely small divergence leads to many applications like surveying, remote sensing, lidar, etc. In this, we see that the light from a torch, on the other hand, in contrast, it diverges primarily due to the fact that the light emanating from different points on the filament propagate along different directions after reflection from a parabolic mirror. Now, if we see this filament lamp, we uh, realize, as in our day-to-day life, that number of point sources and the light emanating from different points on the filament travel along different directions, and if the linear dimension of the filament is less than 2 millimeter, and if the focal length of the convex lens is 10 centimeter, then the angular divergence theta is approximately 1. This divergence could be reduced provided we reduce the dimension of the filament, but the amount of light will also get correspondingly reduced. Now, compared to the filament, the divergence of the laser beam is primarily diffraction. For most laser beams, the spot size, that is the radius of the cross section of the laser beam, is about 2 millimeters. If the laser beam has a free space wavelength of lambda 0 is the free space wavelength, and the spot size is W that we have seen in the last lecture, then the divergence angle must be equal to lambda 0 by pi is the spot size W 0, and this is pi. For a typical spot size of 1 millimeter and wavelength of 0.6 micrometer, the divergence angle of the order of 0.01. A beam is said to be diffraction limited if it diverges only due to diffraction, and usually laser beams are diffraction limited. There are number of causes of diffraction, and one is the number of causes of different divergence, beam divergence, but diffraction is one of those. So laser beam, it diverges only due to diffraction. Now, uh, from for example, from a laser diode, it has a significant divergence due to the small spot size. At the same time, unlike the case of the torch, the divergence of the beam can be reduced much by using a lens in front of the laser diode. Similarly, what is tight focusing? Tight focusing term is related to because of the high directional properties of laser beam, they can be focused to a very small areas. This limits to focusing are again limited by diffraction effects. Smaller the wavelength, smaller the size of the focused spot that we have seen here in this equation. This property leads to application in surgery as in ophthalmology, material processing, series, etc. Now, when a convex lens, using a convex lens, images and a parallel beam is focused like this to a spot. The size of the image point is directly proportional to the wavelength of the light. This is due to the uh, aberration, you know, and the ratio of the focal length to the diameter. That is, the size of the image point is directly proportional to the wavelength of the light and to the ratio of the focal length to the diameter. The ratio of focal length to the diameter of a lens is also called the f number. This parameter is used in specifying the quality of camera lens. Thus, the f by 2 lens f by 2 lens implies that the focal length of to diameter ratio is 2. If the focal length of an f by 2 lens implies that the focal length to diameter, if the focal length of this camera lens is 50 millimeter, then its diameter must be 25 millimeter. Now, smaller the f number for a given focal length, larger is the diameter of the. This increases. This also. Smaller the wavelength, smaller the spot size. That we have seen here. Here for same this thing. And similarly, the smaller the f number. No, smaller and similarly smaller the f number, smaller the image size. Since an object can be considered to be made up of points, if we consider imaging by the convex lens, the resolution provided by the lens will depend on the f number and the wavelength. Two waves. For a given wavelength, for better resolution, we must have a smaller f number. Thus, when a laser beam is allowed to fall on a convex lens, then the radius of the focused spot is directly proportional to the wavelength and the f number. Provided the laser beam fills the entire area of the lens, if we take a lens having an f number of 2, the focal length is twice the lens diameter. Then for example, f, that is, then for a laser of wavelength in nanometer, the focused spot will be 1.5 micro. Thus, the area of such a focused spot would be about 7. So, this is the radius, and this is the area. If the laser beam has a power of 1 megawatt, that means it has to power 6 watt. When the intensity of the focused spot would be approximately terawatt per square, because I by such intensities of light lead to electric fields of the order of such high electric fields. Now, such high electric fields can create a spark in air. This allows the laser beam, because of its high direction, focused to extremely small regions, producing very high intensities and electric. When the electric fields are very high inside a medium, the light can change the properties of the medium. Such effects are termed as nonlinear effects, and we shall discuss them in detail. See, when we see a laser beam, always we should keep precaution. Why? Because even if there is a lens in our eye, and even if its voltage is small, the intensity after passing through this region eye can be much enhanced, and it can damage the. Now, other properties we shall discuss at length in our next lecture.